All right, I'm going to answer the remaining questions in one video here. So number 19, name the two pathways by which NADH electrons from the cytosol can enter the mitochondria. All right, the two pathways are the glycerol 3-phosphate shuttle and the malate aspartate shuttle. Now, these two shuttles are functionally different in that the glycerol phosphate shuttle takes the NADH and the electrons from NADH are actually transferred to an FADH2. So energy is actually lost using the glycerol 3-phosphate shuttle, but because its energy is being lost, it's actually energetically downhill, and so it's perhaps the more favorable or more spontaneous of these two processes. The other shuttle is the malate aspartate shuttle, and it's a more complicated shuttle, but it has the advantage that NADH on the outside of the mitochondria is turned into NADH on the inside of the mitochondria. There's no net free energy change, at least standard free energy change with the malate aspartate shuttle. So those electrons from NADH can be turned directly into NADH in the inside of the mitochondria and used for the electron transport chain. All right, number 20. How does the ATP-ADP translocator work? And this actually ties in nicely with number 21. All right, so mitochondria has these two membranes, the outer and the inner membrane. And the electron transport chain is continually pumping protons into this inner membrane space, the region between these two membranes. So the end result of this is that the inside of this inner membrane space has a lot of protons, first of all, and is relatively positively charged compared to the mitochondrial matrix, which is the inside of the mitochondria. All right, now because of this charge difference here, that charge difference is actually what drives the ATP-ADP translocator, because if we compare ATP and ADP, right, they have different numbers of phosphates on them. So ATP having 3 phosphates actually has a negative a charge of approximately -4. ADP, since it's lacking one of the phosphates, only has a charge of -3. Now, ATP is being produced inside of the mitochondria, and it wants to get out to the rest of the cell. So ATP wants to leave. Similarly, in order to continue producing ATP inside of the mitochondria, we need to bring the spent ATP back into the mitochondria so it can be turned into ADP or ATP. All right, so we want the translocator to work in this particular fashion. Now, does this make sense based on the charges here? Well, anytime we allow an ATP out and an ADP in, we are actually transporting a net of 1 negative charge out of the mitochondria because ATP is slightly more negative than ADP. So because of this, this whole cycle now is very favorable because we're balancing out the positive charge in the inner membrane space. All right, another way you can kind of explain this or think of it is that the movement of ADP into the mitochondrial matrix is pretty unfavorable because ADP has this charge of 3 minus and it's going into a region that's negatively charged here. So that is a very unfavorable transport for ADP to be able to enter. But for ATP to be able to leave is extremely favorable because it has a net charge of 4 minus, a very negative charge, and it's going to a very positive area in the inner membrane space. So the thermodynamically favorable movement of ATP into the inner membrane space drives the thermodynamically unfavorable movement of ADP into the matrix. All right, now question 21 here asks how brown fat produces heat. All right, now the way brown fat produces heat is using this proton gradient. Because what brown fat has in it is it has a transporter here called uncoupling protein, UCP1. And what uncoupling protein does is it allows these protons in the inner membrane space to simply re-enter the mitochondrial matrix without any energy being being transferred to anything like ATP or anything like that. The protons are just simply allowed to go back to where they came from. Now, what's the end result of this? Well, that the thermodynamic or the electrochemical gradient here is being dissipated. So that energy that we've built up is now just simply being released, and we're not making any chemical energy from it. So that energy has to be given off as heat. In addition, because now the proton gradient is lower, this actually leads to now the electron transport chain wanting to work in overdrive. It wants to use more NADH and and more oxygen to generate NAD plus and water. And so it wants to basically try to restore this proton gradient, so it turns on the electron transport chain as well. So now we're burning even more of these reactants with the electron transport chain. But again, the product, the proton gradient product, is simply allowed to dissipate, giving off heat. And so that's how brown fat is able to produce heat. And that is it, I believe, now for this problem set.